Okay, so today's notes is going to be on Venn diagrams and set operations. All right, with the Venn diagram. Venn diagram is hopefully something you've heard before. All right, a Venn diagram is basically just a visual representation of a large set with its smaller subsets. All right, we usually, not always, but typically, we draw a universal set as a rectangle. And then inside the universal set, we do Venn circles. All right, usually they're overlapping because a lot of times our subsets are overlapping. Not always, but a lot of ours are. And hopefully you've seen Venn diagrams before. It's used in a lot of things, not just mathematics. All right, so Venn diagrams are kind of a common one. All right, so I'm going to draw a Venn diagram and then put the appropriate number, integer, in the right region. Alright, so my universal set is the numbers 1 through 9. A is the numbers 2, 4, 6, 8. B is the numbers 3, 4, 7, 8. Draw the Venn diagram using the sets above. Place the numbers in each appropriate region. And again, see if you can do this on your own. Right? If you're familiar with Venn diagrams, you should be able to do this as I'm doing it. Alright, so this would represent my universal set, so we would label that U. Inside U, it's got subsets. There's subset circle A and subset circle B. Alright, and then so these would be the different regions. Alright, A and B are in, all of the numbers are in, they're all subsets of U. So circle A is completely in U, circle B is completely in U. And then there's a little region here where we've got overlap. Alright, and there's some, the overlap could be empty, no set, empty set. But there could also be numbers that land in both the subset A and the subset B. And that's what we're going to do. We're going to put our numbers in. Alright, so in circle A, we've got 2, 4, 6, 8. B, we've got 3, 4, 7, 8. I always start with the middle, and so they share 4 and 8. Alright, so 4 and 8 are in both the universal set and both subsets. Alright, so 4 and 8 go here. Alright, then I'm going to look at circle A. So I've already counted 4 and 8, so they're already here. I don't want to put them in again. Right, there's only one 4. Right, it happens to be in the universal and in both my subsets. 2 is also in my universal and subset A, and 6, alright, so 2 and 6 are counted for. Now I do B, I've already counted 4 and 8, so I still have 3 and 7. I'm not done yet, right? My universal set has to have all of the numbers, digits, between 1 and 9. Well, I haven't put all of them in there, right? Because there are some of the digits in my universal set that are not in subset A and not in subset B. And those ones that are not in subset A, well, 1 is not an A or B. 2 is, 3 is, 4 is, 5 is not in subset A or B, 6 is, 7 is, 8 is, 9 is not. And then I check to make sure I've got all my numbers, right? My universal set has to have everything that's included and included once. There's only one number 2, there's only one number 4, it just happens to show up in 4 spots. All right, in 4 happens to show up in circle A, circle B, and the universal, but there's only one number 4. Alright, so I'm going to check 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Alright, that's my universal set. Alright, so that's what we mean by the Venn diagram. It's a visual tool that we use, and we'll do applications that involve Venn diagrams. We'll put numbers in and how many land in each region. Alright, so we'll do more with Venns later on in this section and in 6.2, we'll do applications with Venn diagrams. Alright, first though, operations. Alright, so these are some of the things that you need to make sure you're familiar with. You need to make sure you understand what they are and to recognize the symbols. Remember, math is a language and there are symbols that we apply. Like the plus symbol means add, minus means subtract. Alright, and so we've got operators for sets. Alright, the first operator is the intersection. Alright, the intersection between two sets, set A and B, is the set of all elements belonging to both sets, meaning it's only those elements that are in both A and B. Alright, so the notation, and then we'll get to the Venn diagram. Alright, so the notation for the intersection is A, and then it's sort of like this upside down U, B. And again, this stands for and, right? The word we use is and. Elements in A and B. Alright, I'm going to write my A and B sets that I had earlier. So A was the set 2, 4, 6, 8. B was the set 4, 3, 7, and 8. All right, and so everything that was in A and B, well, remember, everything that was A and B was what they share. They share the number 4 and the number 8, and so this would be the set. I can draw my set notation better. 4 and 8. All right, and so the Venn diagram is that overlap area. All right, so this would be my universal. I've got my circle A, I've got my circle B. Remember, 4 and 8 showed up in this region. That's the region. Anything in that area is in both set A and set B. That's the intersection, right? The overlap of my two. All right, and so that's what we're talking about when we're talking about the intersection. All right, and so the symbol you need to recognize is that, and it stands for the overlap, or the intersect, right? Intersection makes sense where the two sets intersect. All right, the next one is union. All right, the union of set A and B. All right, so the union is the set of all elements belonging to set A. So anything that's in set A, anything that's in set B, or anything that they share in common. Biggest thing with the union is you don't want to count anybody twice. It's just all of the elements in one or the other. If they happen to share some, well, those are included, but we only include them once. All right, the notation for the union is the flip of the intersection, is sort of the U symbol. All right, so this would be the or is all inclusive. Everything from set A or set B, and it does include anything that they share in common. All right, biggest thing is it only shares one. There's only one number 4 that they share. All right, so remember, set A was 2, 4, 6, 8. Set B was 4, 3, 7, and 8. All right, so the or would be all of the digits. So 2, 3, 4, 6, 7, and 8. All right, would be all of the ones that are in one or the other. There's only one 4 and only one 8, even though they share those, right? They share 4 and 8. And I wrote them in order. You could write them out of order is fine. Remember, equality doesn't care what order it's in, just as long as it's all the elements are included. So as long as you have a 2, 3, 4, 6, 7, 8, doesn't matter how you list them. All right, so the or, the union, is everything that's in either A or B. All right, it's all inclusive. All right, and so this would be set A, set B. It's everybody in this circle and everybody in this circle, including anything that they shared in common. All right, so that's the union, right? Union means all inclusive, all of the elements that are in both A and A or B. All right, A or B. My complement, we like the complement, especially when we get to some of the stuff we're going to do later this semester, and then when we get to counting and probability. Sometimes it's easier to find the complement of what we're looking for, right? The complement sometimes the easier one, and we use that to find what we're looking for. Or it's easier to find what we're looking for by finding the complement and throwing it away. All right, so the complement is what it seems. It's anything in my universal set that's not in set A. If set A is the one I'm looking at. All right, so I have set A. I've got my universal set. The complement of set A is all of the elements from my universal set that are not in set A. And so the notation for this is we put like what's considered in mathematics a prime. All right, A prime, that means not in set A. All right, so if you remember, set A were the numbers 2, 4, 6, and 8. The universal set was the numbers 1 through 9. And so the complement set would be everything from my universal that's not contained in set A. And so it's basically the odds, right? Because set A is the even. So it would be 1, 3, 5, 7, and 9. And double check and make sure I got all of the odds. All right, and that would be everything not in set A, and that would be the complement. All right, so when we're drawing the Venn diagram, remember it's my universal. I've got set A here. I've got set B where there's some overlap. Everything that's not in set A, and it can be in the part that's in B, but the part that is B that's not in set A. So it would be all of this area outside my set A circle. Right? That's the complement area. Right? Basically, I would hide set A, anything in set A, and then I'd be left with everything outside of that. And the numbers, if we go back and look at the Venn we did before, those numbers should be 1, 3, 5, 7, and 9. Alright, this is also important. Kind of like the complement's a big concept that we're going to be using, especially when we get to... We're eventually going to count big sets, like the things that are in the hundreds, thousands, even millions eventually. And so sometimes when we get to those big sets, it's easier to find complements. Also, when we get to counting big sets, it's going to be nice when we have sets that are called disjoint. Alright, disjoints are nice. Alright, so it's important that we can recognize them and understand what it means when we say set A and set B are disjoint. Alright, so disjoint sets have no elements in common, meaning the intersection is empty. There's nothing in the overlap. Alright, the notation for this would be the set A and B is the empty set. Alright, there's nothing shared by set A and set B. It's the empty set. And so if we were drawing a Venn diagram, there's two ways to do that. You can either draw it where they overlap, but this is empty, there's nothing in there, or sometimes we draw it, well, since there's no shared elements, we just draw the two sets separate, right? Because there is no overlap, and either one of those are fine, all right? You can either draw them where the overlap is empty, or draw them completely separate, means disjoint either way. And we like disjoint sets. Alright, the last set rule, alright, is the Cartesian product of two sets. Alright, it's denoted A times B. It's the A times B. It's all ordered pairs. So what we're doing by the Cartesian product is we've got two sets. We've got set A, we've got set B. And what we're going to do is, well, we're going to pair them together. Meaning that's going to be whatever it is we're counting. We're counting a pair of things, a group of things. Alright, and we'll do this a lot when we do experiments. For instance, suppose I roll a dice and I want to roll the even numbers. And so I've got my set A are the even numbers on a dice. 2, 4, and 6. Right? The numbers on the dice are 1 through 6. And so the even numbers would be 2, 4, and 6. And then I'm going to flip a coin. Alright, flip a coin would be set B, which would be heads. And I'm just going to do capital H for heads and capital T for tails. Alright? And so when I'm done with the experiment, I've got a number from my dice, and I've got either heads or tails from my coin, and that's one group. And so we pair them together. Alright, and so the first thing we do is the roll of dice, so that would be the first thing in my set, which comes from set A, so it would either be 2, 4, 6. And then the second thing we do is we roll our dice, and that would either be heads or tails. And then so one outcome would be I roll a 2, and I flip heads. Alright, and so all possible outcomes in my experiment, where I'm combining these two things, would be I can get a 2 and a heads, or I can get a 2 and a tails, I can get a 4 and a heads, or I can get a 4 and a tails, I can get 6 and heads, or I can get a 6 and tails. And when we do experiments later on, a lot of them are going to end up being Cartesian product, and we could do Cartesian product with more than just 2 sets. We could do 3 sets or 4 sets. They just have a bigger group. When we go to roll dice and flip coins, this is often how we'll do things. All right? And the reason why it's called a Cartesian product is because that's how you end up counting it. All right? How many pairs do I have here? Well, I have 6, right? There are 6 outcomes possible in my Cartesian product. Well, I had 3 elements in set A, 2 elements in set B, and so if I multiply 3 times 2, I know there should have been 6 pairs. Again, when we eventually do this with other things, that's the rule we're going to use. Alright, so again, make sure you familiarize yourself with the set operations. Alright, so make sure you understand the different set operations, union, intersection, complement, and the notation that goes with them, because basically, union, intersection, and complement will be used over and over and over again in Chapter 6, over again in the next chapter, and over again in the chapter after that. Alright, so basically we'll be using the same concepts for the next 8 weeks. Alright, over the first 3 tests, you'll be seeing symbols or terminology for union, intersection, and complement. Alright, so the next and last video from this set of notes is then just going to be practicing finding different sets using the union, intersection, and complement rules. Alright, so we will wrap that video up there.